What I like to say is anything that creeps, crawls, moves, flies, does any movement of any kind in any liquid, air, water, whatever it is, we can simulate it. You're using computers to solve the equations of motion. When you solve these equations, you will know pressure and velocity at every point in the flow field. I'll take a case of a plane. So at every point on the plane, you can calculate what the pressure is. You integrate that pressure force over the entire plane. That will give you the drag force on that particular object. So when the 787 came along, for example, that was designed almost entirely using CFD. That is the power of CFD to be applied to aerodynamics problems. So you can apply that to planes, you can apply that to trains, you can apply that to trucks, it doesn't really matter. In CFD, you can reproduce conditions exactly. The level of detail you can get from it cannot be matched by anything else. You will reproduce the solution you had every time. You can run either the model scale as it is if you want to compare to the internal data, or you can run full scale, which is the real thing. So when you're running full scale, the drag you get is the full scale drag. There's no need to scale it by any means. There's no need to do any kind of scaling. You're getting the real number. So you can compare more directly to what you see in real life. CFD started out in high-speed aerodynamics. It hadn't been used for very low-speed flows. First, you have to crawl before you can walk, you have to walk before you can run. So that's the way CFD has been. But as time has gone by, resolutions have improved, methods have improved, accuracy has improved, and it has been validated for a huge number of problems.